Automated program verifiers try to automatically check whether a source program is correct or not with respect to some specification. Many automated program verifiers are translational verifiers. That means they first translate the source program via so-called front-end translation into an intermediate verification language, which I will abbreviate as IVL. And this IVL program is then handed to an IVL backend verifier, which tries to automatically check whether the IVL program is correct or not. The advantage of this setup is that program verifiers for different source languages can reuse the same highly optimized IVL backend verifier by targeting the same IVL. An example of a widely used IVL is Boogie, and there exist various front-end translations from different source languages into Boogie. 3 examples of such source languages include C, Daphne, and Viper. So for verification results to be meaningful in this setup, it is crucial that soundness holds. That means whenever the IVL backend verifier reports success, then the input source program should indeed be correct. Because the front-end translation and the IVL backend verifier work very differently, it is natural to split the soundness property into 2 parts, namely the front-end soundness and the backend soundness. If you establish both, then you get the desired soundness property. In this work, we focus on front-end soundness, that is, establishing if the IVL program is correct, this implies that the source program is correct. We can combine our work on front-end soundness with existing work on back-end soundness to get end-to-end soundness guarantees, but in this work, we focus on front-end soundness. So a key problem for front-end translations is that their implementations used in practice provide no formal guarantees for front-end soundness. So this is a major issue because these implementations are highly non-trivial and very large, so bugs can and do arise. And the goal of our work is to solve this problem, which we do at the high level using a foundational per-run certification approach. So we add code to an existing front-end translation such that on every run of the translation additionally produces a certificate expressed in an interactive theorem prover, such as Coq or Isabelle, which formally shows front-end soundness. The major advantage with this approach is that it provides formal guarantees to existing implementations. So we're really taking an existing implementation and just adding code for the purpose of generating the certificate automatically. At the high level, we make the following key contributions. We develop a generic simulation methodology relating source language and IVL constructs. This methodology is in principle independent from any specific source language or IVL. We then apply this methodology on an existing front-end translation, namely the translation from the source language Viper to the IVL Boogie. So Viper is a verification-aware language with separation logic reasoning, and Boogie is a widely used IVL. And using this methodology, we're able to realize the approach that I showed on the previous slide. So we add code to the existing Viper to Boogie translation such that on every run of this translation, it produces automatically an Isabelle certificate showing front-end soundness. I want to emphasize 2 things here. Firstly, the generation of these Isabelle certificates is fully automatic. And secondly, this Viper to Boogie translation is an actively maintained and used tool which existed before we did any work. And so before we did anything, this was 8,500 lines of Scala code, and we left this code largely unchanged and just added code for the purpose of generating these certificates. Finally, we evaluated our certifying adaptation of the Viper to Boogie translation on a representative set of Viper benchmarks. Our artifact, which includes the certifying adaptation as well as the evaluation, is available online. I want to now discuss some of the challenges that occur when justifying front-end translations. I will illustrate them for the sake of concreteness based on the source language Viper and the IVL Boogie, but these are challenges that apply to front-end translations in general. So the first challenge is the semantic gap between the source language and the IVL, which is very large. As an example, for Viper and Boogie, the state models are very different. So Viper has a built-in heap and also tracks permissions for heap locations, while Boogie only has a simple variable store. The execution models also differ significantly. So in Viper, expressions can fail to evaluate, for instance, if there's not sufficient permission to a heap location that is being read. Statements which operate on separation logic assertions are also complex in Viper, while in Boogie, expressions never fail to evaluate and statements are very simple. Finally, Viper is based on a flavor of separation logic, while Boogie does not use any advanced program logic reasoning. I just want to make now some of these points more concrete by showing you an actual example. So here you see a Viper exhale statement on the left and the Boogie code that is generated on the right by the existing implementation. So an exhale statement takes as input a separation logic assertion, and it checks whether this assertion is satisfied in the current Viper state. If it's not satisfied, the exhale fails, and otherwise it removes the permissions specified by this assertion. The details of this exhale are not so important here. The key point is this is a complex operation that must be reflected in the Boogie code, where Boogie does not have any built-in notion of separation logic. I will now just outline some points in the Boogie code regarding the semantic gap. So first, the Viper state, which consists of a heap and permissions for each heap location, is modeled explicitly in the Boogie code via two separate Boogie variables, one modeling the heap, one modeling the permissions. So these are basically Boogie maps. Then you can see a bunch of assert conditions in the Boogie code. These are encoding when the separation logic assertion is satisfied. So these are non-trivial in general. Finally, in this highlighted part, you can see that the Boogie code is using axiomatization. So there's a Boogie function ID on positive. This has no body, but is constrained by a Boogie axiom, which is also part of the Boogie program. It's not shown here, but when you reason about the translation, you need to take this axiom into account. This is another example of a semantic gap because on the Viper side, there is no axiom or function. So I want to show now one more challenge based on the same example. And so this is, if you look at these two highlighted parts, the current Viper to Boogie translation omits these under certain conditions, because under certain conditions you can show that they're actually not required. And so this is really a challenge that appears for implementations that are used in practice which want to optimize the encoding as much as possible. And so the general challenge here is dealing with diverse translations for the same construct depending on the context where different conditions may hold. I want to now move on to the final challenge, which is non-local reasoning. So in Viper, you can define methods which have a precondition, a postcondition, and also a method body. Each Viper method is translated to a Boogie procedure, and the Boogie procedure encodes two things. So first, it checks whether the pre and post condition are well formed. This is a semantic condition. And secondly, it checks whether the body does not fail and whether the body respects the pre and post condition. Now you can, of course, define a second Viper method that calls this first Viper method M1. Then you get the corresponding Boogie procedure that encodes the second Viper method. And the call to the Viper method needs to be somehow encoded in this Boogie procedure, so the second one. And what's challenging is that the soundness, so this encoding of this call, is sound only if the pre and post condition of this first method are well formed. And this is where non-locality comes in, because to justify the encoding in one procedure, one needs to take into account a check that was done in a different procedure, in this case, checking that the pre and post condition are indeed well formed. And I just want to emphasize that this is yet another challenge that occurs especially for implementations used in practice, which are the ones we're interested in, because the reason for this dependency is actually an optimized encoding of the call. I want to zoom out now a bit, and I want to show you how we automatically generate this, the certificate showing front-end soundness at a high level. And here I will also point out where the challenges appear that I just discussed. So in general, a Viper program consists of a sequence of Viper methods that are translated to a corresponding sequence of Boogie procedures. There's a one-to-one correspondence. And our certificate relates each method with the corresponding procedure by proving the following statement. So if the Boogie procedure body has no failing executions, this implies the condition on the left for the corresponding Viper method. So first, the Viper method specification is well formed. This is the first part of the encoding that I showed on the previous slide. And if all specifications are well formed, this implies that the corresponding Viper method body has no failing executions. So if you can show this for every method procedure pair, then you actually directly get front-end soundness, which in our case is if there are no failing Boogie procedure executions, which is the same as the Boogie program being correct, this implies that there are no failing Viper method executions, which is the same as the Viper program being correct. But the challenge is really this first part, so relating a Viper method with the corresponding Boogie procedure. And in our certificate, this is done via a simulation result, so showing that the Boogie procedure body simulates the corresponding Viper method body. And all the challenges that I discussed appear in the automatic generation of this simulation certificate. So let's take a closer look at the simulation. So let's get back to our original example. We want to show that the Boogie code on the right simulates the Viper statement on the left. And because the exhale is quite complex and the semantic gap between the languages is large, we decompose the simulation into simulations of separate semantic concerns, which together make up the exhale, because showing the simulations of these smaller semantic concerns is easier than doing it for the exhale in one go. So here there's a natural way to decompose. So there's a conjunction, and you can show that you can decompose the simulation into the simulation of the two conjuncts. But we go beyond the syntax. So in this case, we would also decompose each of the conjuncts into separate semantic concerns. So a bit more concretely in this example, we would decompose the simulation of the exhale into 5 separate semantic concerns that are highlighted here, each with a different color, and the Boogie code highlighted with a particular color is simulating one particular semantic concern. So for instance, here, the first 2 semantic concerns are simulating the simulation of the first conjunct. The next 2 semantic concerns are simulating the simulation of the second conjunct. And the final part below in violet, this one is simulating just the finalization of the exhale that always happens at the end. So at the high level, our proof automation strategy for automatically generating this simulation certificate is to decompose the simulation into small semantic concerns. So the decomposition follows fairly naturally from how the Viper semantics is defined. And then we use Isabelle tactics to discharge the simulation of the resulting small semantic concerns. So our paper outlines much more about how we do this exactly from a technical standpoint. Moreover, the paper also talks about how we deal with the diversity and non-locality challenges that I discussed at the beginning. And if you're interested, I refer you to the paper, but I now want to move on to the evaluation. So we evaluated our certifying adaptation of the existing Viper to Boogie translation on 72 representative Viper programs, and the corresponding 72 automatically generated certificates that show front-end soundness were all successfully checked by Isabelle. To give you a bit of an impression of some of the numbers here in these programs, I'm just showing 6 of the larger examples from these 72, so you can see the size of the Viper code in lines, the size of the Boogie code, so the translation, the size of the Isabelle certificate that we generate, and finally the time it takes to check the certificate. It checks Isabelle to check the certificate in seconds. And so if you just focus on the last column, you can see that these times are not short, but we believe a natural workflow is to generate and check certificates just for final release versions or as part of continuous integration. So we believe these times are acceptable. And all of this is also available in our artifact. So I would like to conclude my talk by just saying there's a lot more regarding both of these boxes here in our paper. And if you're interested, please read our paper. Otherwise, I'm happy to take questions now. Thanks.
If you have any questions, please come to here and ask questions here.
Yeah, hi, thanks for the talk. That sounds all pretty cool. So I was wondering, you mentioned in the beginning that the translator was 8,500 lines of Scala before you did your work. So could you give us an idea for how much code you had to add, and also in terms of long-term maintenance of this, as presumably this translation will keep evolving, Viper gets new features or existing things get refactored. Is there any way to quantify or hypothesize how much having this certificate around will impact the future development of that translation?
So there are two parts to what code we added. So we added code for the purpose of generating more information so that we know what proof to generate. This is really within the translation that's already defined, and there we just add around like 300 lines, so not much. This is just like hints and stuff like this. And then we take these hints and then transform them into a proof, and this is largely boilerplate code. This I don't know how much it is, probably maybe 1,000 or more. So I would say this is around the size of the code. And regarding how the development will change, so we definitely want to keep evolving the certificate generation, also extend it to a larger subset. So I think it'll be harder to develop fast in the sense if you want to keep the certification at the same level. So there I think I don't have enough experience to say how it will evolve exactly, but in my experience, the certification really informs the development in the sense whether you know whether the transformations are correct or not. So I think this is the main impact, but how it will really impact the development, I'm not sure. I think one could probably have like two versions, a fork that is that uses certificates and one that's just normal, and then one lags behind a bit. But I think keeping them up to date at all times might impact development speed a bit too much. But the goal would be to have certificate generation with always with the newest features.
Okay, cool, thanks.
Just interested, did you tailor the Isabelle kind of tactic setup for each of the different segments of the code you were trying to prove?
Yeah, so we have two different approaches. So one is more agnostic towards what segment we are trying to prove. In other cases, we have more specific lemmas that we show which are more useful for certain segments. So we have a bit of both.
And did that give you a big runtime impact, like when you really tuned for particular code snippets and things like that?
Yeah, I think if you tune it for something, then you can definitely get speed ups there, but we have not yet invested much time into optimizing the proofs.
So holding mic, I'd like to have a question. So how much complex this Viper program can be? How much complex program can be automatically verified in your systems?
So I'm not sure what you mean. So in our case, the generation of the certificate is always automatic, no matter how complex the Viper program is, at least in our subset. We just don't support the entire Viper subset yet, and I think increasing that subset will make Viper programs more complex, but the goal will be to keep this automatic all the time.
Let's give him a big clap.
Thank you.